your practice or exam study resources on Friday, so you have the weekend to start. You got to dig into those early and get your questions answered. Maybe we can do the same kind of study session Thursday, and I expect to see a lot more of you there this time instead of recitation. So next a week from Thursday. Okay, we'll talk more about that as it gets closer. But many of you need a new approach to this third exam compared to second exam. You need to really dig in early, study hard. Then you'll have the time to get your questions answered. Okay. All right, let's look at number 3. So this is the ones you're having the most difficulty with. So what's the key to succeeding at this problem? No, nothing to do with polar. Drawing it, making an illustration, right? These are what kind of problems? Geometry problems. These limits of integration for double and triple integrals are geometry problems. So we need to figure out what this thing is. This E, right? We're trying to figure out what E is. It's bounded by the cylinder, planes x equals 0, y equals 3x, and z equals 0 in the first octant. Okay? So what is x equals 0, first of all? What is x equals 0? That's the YZ plane. The plane of, say, the screen or the plane of your page, right, is the YZ plane. So that's going to be one of the boundaries of this E. Y equals 3x. So x equals 0 is this plane, like the plane of the screen. Okay? Yeah. What about y equals 3x? Vertical plane, right? Vertical plane along. So this is x and y, so we should be able to imagine that is in the first octant is like this. And what that's going to extend up. So we got the plane back there, the plane of the screen. We got this plane, y equals 3x. Z equals 0 is what? It's easy. That's the floor, right? The xy plane. So we know we're going to be above that. If we're in the first octant, we're going to be above that. And so finally then, so let me draw x equals 0 back here like this. So we know we got the floor is z equals 0. We got this y equals 3x, x equals 0. And then finally, the cylinder, y squared plus z squared equals 324. So what's that? Cylinder down x, right? And then r equals 18. So maybe I'll just put 18 here. So in the first octant, do something like this. So now, what is the solid bounded by all those things? So the bottom of it is this down here, right? That little wedge. The back of it is there. So what happens when y equals 3x cuts through this cylinder? What's that going to create? You see, that'll create like an edge like this. That's like the intersection of that cylinder and y equals 3x. So I think we've got it. So I'll outline the whole thing in red. So it's going to be like this, and like this. There's back in the x equals 0 plane. And then back there also. So I've outlined the whole thing. Does it show up red on the screen? So I've outlined the whole thing in red. So those who were struggling on this problem, was that part of the difficulty getting the right E? Did that help? I mean, besides the fact that I did it, so does it help you be able to do that in the future is the idea. So that's the E solid. So like we worked on in the first couple exams, these surfaces are important. Now we've got a bunch of surfaces and we're trying to put it together to make the boundaries of a solid, so we've got to really know those surfaces. Can you take it from there? So then you've got your choice, right? You can choose what we're calling type A, B, or C. They don't. All you need to do is finish the problem, and then your integrand is Z, right? The integrand is Z. So those who are still haven't succeeded on this one, does it help? Any questions? Can you take it from there? Okay. So let's go back to I mentioned, and someone mentioned this, using involving polar in these triple integrals. So the way that comes into play is actually we have a new coordinate system that's kind of like polar. All right, and so this is called what's called cylindrical coordinates. So instead of Cartesian coordinates, which is x, y, and z, all based on like right angle distances, right? Perfect. Okay. So so our Cartesian coordinates x, y, and z are just all based on right angle distances, right? Z is distance up and down. X is distance in and out of the page or the screen, and y is distance right and left. So it creates like boxes, rectangles, right? Rectangular coordinates. So what are cylindrical coordinates? Cylindrical coordinates okay. Cylindrical coordinates, so instead of x, y, and z, we have r, theta, z. So r and theta are the same coordinates as in polar. So it's like the xy plane is now transformed into the polar coordinates. And then the z coordinate is the same as the z coordinate before. It's just up and down. All right, yeah. So r is supposed to come out. Anyway. So r is in the xy plane is the distance from the pole, right? In the xy plane. Okay? And so here I'm showing r increasing there, right? So increasing, say, and then theta is our standard trig angle, right? It's our standard trig angle counterclockwise from the xy plane. This is not really working very well. Okay, and then z is distance up or down. So it's like when you change z, you just take the polar plane and you move it up or down on the z-axis. Okay, so here's an example of the point 4.3, 2.4, and 8.25. So 4.3 meaning this blue segment right there is r is 4.3. 2.4 is the number of radians. That's radians swept counterclockwise from the positive x-axis. And then we're up above the xy plane 8.25 units. That's our z value. Just go ahead and practice, plot these points. So just practice plotting those points in cylindrical coordinates. Cylindrical coordinates. And then sketch. What would these be? plot 3 points and sketch the representations of these 3 statements. R equals 4, Z equals 2, theta equals 5 pi over 6. What would those mean? All right, here's the first one. So what? R equals 2, so this distance here is 2. This is our angle pi over 4, so we're in the first octant and we're up 1. Make sense? All right, what's the next one? R equals 1. It's going to show up. Okay, and then theta equals pi. So we're back over there. And then we're up higher. Z equals 3. So we're up higher. So that's that one. 3, 7 pi over 4, negative 1. So where's that? That's below the xy plane. 7 pi over 4 is around here somewhere. And 3, so further away like this. So we're 1 beneath the xy plane. Angle 7 pi over 4, 3 away. So r is like the horizontal distance from the z-axis, right? R is like the horizontal distance away from the z-axis. Okay, what about these other things? R equals 4. What will R equals 4? How will that graph? There's lots and lots and lots of different kinds of cylinders, right? So we said cylinders, there's any curve, you can start with any curve and extend it and you get a cylinder. So, right, circular cylinder. So let's graph that with radius 4. So that's just a cylinder with a circular cylinder with the z-axis as the central axis, a vertical cylinder. What about z equals 2? Horizontal plane at height 2. It's the same z equals 2 in Cartesian coordinates. What about theta equals 5 pi over 6? Okay, so is it a plane? Kind of. What's that? Yeah, it's like half a plane, right? Because so in cylindrical coordinates, we don't really consider negative r's the way we did in polar coordinates. Remember in polar coordinates, we could go at some direction, and negative r would be back 180 degrees or pi from that direction. So in cylindrical coordinates, we really just deal with positive r and angles from 0 to 2 pi. We don't go beyond that angle, and we don't use negative r. So if you just, under that, 5 pi over 6 is just really pointing in this one direction here, away from the z-axis, and we don't consider negative r back here. So what we do, we get like half a plane. So let's see if it'll show up here. Yeah. So we get like half of a plane. Where is that pointing? Is it pointing in the right direction? 5 pi over 6 should be almost to the back. It doesn't look like it's right. This is not my day. Let's see now if it's pointing in the right direction. Okay, yeah, this. Okay. So that show a little bit less of it. We got it. But the point is, it's like it's a plane that has a boundary on one edge, right? And just extends in that direction. Okay, so let's talk about now then what would triple integrals be? Well, if you know polar coordinates and you know your basic rectangular triple integrals, there's not much more to talk about. It's pretty straightforward. But let's just write it out anyway. Any questions so far? So triple integrals. Okay, so basically, we don't really work at changing order too much. We're going to use our rectangular variable first, and normally that's z. So first of all, our function, we could have a function of r, theta, and z. And so we're gonna like a type A triple integral, we're gonna do dz first. And so that's gonna go from that could be some function of r and theta, or a bottom lower to upper. And then from there, what do we do from there? Well, we're going to project into the horizontal plane, which is now the polar plane. So we're going to have a double integral, like a polar double integral. Okay? So what is that? That's like r1 to r2, and theta 1 to theta 2. And so we project the solid into the horizontal plane, which then we treat as polar. And so when we treat that as polar, our dA is? Yeah, we got the r. Remember we showed where that r came from, r d theta. Because theta is not a distance, right? Theta is not a distance, so we need that r in there to get the actual arc length. R d theta is like a little arc length, right? And then the r, it comes with the polar dA, and then it links up with the function and multiplies them with the function when you're solving these, okay? So we have our relationships. They're all the same as before. R squared equals, what's r squared equal? X squared plus y squared. So all the same polar relationships hold. X equals r cosine theta. Y equals r sine theta. Theta is, in terms of x, y, and z, arctangent of y over x. Same as before. But just remember, if you're ever using that, if you're ever using arctangent, just remember the range that you're going to get are going to be values between negative pi over 2 and pi over 2. And you might have to adjust based on if the angle you want is outside of that range. And you have to take that answer from arctan, which will be in this range, and make whatever adjustment you need to get the angle you have in your situation. So just be careful with the range thing with if you're ever using arctangent to make transformations of coordinates here. Okay, so Julia's question, we could have something like a cylindrical coordinates, say along the y-axis. Well, then we're going to do dy r dr d theta, and our theta then would be, so this is the xz plane, right? So then looking this way, our theta would be counterclockwise from the positive x-axis going like this, right? So our theta would be in the xz plane, but it would still be the standard trig angle, but now in the xz plane. So that would be dy r dr d theta, where the r and theta are transformed polar plane from the xz plane. Okay. So there is actually a homework question due tonight that's actually along the x. Let's just talk about that one more. Talk about that. Is that number 2? There's kind of 2 issues with number 2, so let's talk about both of them. So this one. So our region, our solid, x equals 9y squared plus 9z squared paraboloid opens, how does that open? Positive x-axis. And is it circular or elliptical? Circular, because these coefficients are the same, right? If you divided by or multiplied by different values, then you'd have elliptical, right? So we have this circular. Anyway, this circular paraboloid. Like that. So it's like a tip of a rocket or something that's crashing into the origin. Okay, and so the question is, wants to evaluate this triple integral, and so what could we do here in terms of order of integration? So what could we think of in terms of order of integration? We're going to evaluate x dv. So what should our dv be? We're going to make this as easy as we can on ourselves. So dx, so we're going to go from what to what when we do dx? Back to front. So the archer's back here. He's going to shoot into this thing, and he's going to hit the what first? Paraboloid, always? Yes. And then it's going to exit out the plane, always? Yes. So where we just got one triple integral here, as according to the inside, it's always going to, the back is always the paraboloid, and the front is always the plane. So we're going to do that, and then from there we're going to do r dr d theta, where now our polar plane is in the yz plane. So our theta would be this angle in the yz plane, like swept. And this would be r. So now your polar plane's the yz plane. So theta is swept counterclockwise from the positive y-axis. R is distance from the pole and the yz plane. And then this outer double integral is going to be based on the projection of this thing into the yz plane. And what will that be? When we project that solid into the yz plane, we'll get a disk, right? We'll get just this filled in circle. And that's super easy when you have to do r and theta. Questions on this example? Yeah?
Do we have to change the function f that we're integrating over?
Yeah, now in this case, x is one of your variables, right? So if this were like x, y, and z, then you have to get your y and z. X is a valid variable because we're doing dx. So in this there's nothing to do on this one. But you're right, if this function had y's and z's in it, then you'd have to convert your y's and z's into the corresponding r and theta relationships according to polar. Does that answer it? But here you don't have to do that because you just are integrating x, and that's one of your variables. Yeah, so if you had y's and z's and you converted it to x, r, d, r, d, theta, then all your y's and z's would be according to what? Y would equal what? And z would be what? Y would be? That would be your r cosine theta, because y now is your horizontal coordinate and polar. And z would be? Z would be your r sine theta. For polar in the yz plane. Okay, questions on this example? Does it make sense? Okay, so we need something. We'll do something easy and something hard. So easy, we'll do what we did last time, and that was the closed it. Sheared cylinder. So this thing. So this is easiest in cylindrical coordinates, right? So we were setting up, we set up a bunch in rectangular coordinates. You're going to be doing dy, dx, dz, rectangular coordinates. But now, so the easiest, most efficient way to solve this is cylindrical. Go. You have 2 minutes. Don't just set it up. Just set it up. You don't have to solve anything. All right. Let's see who. Richard, did you get it? Tell me. 5 minus r sine theta. Okay. Okay, and then we're going to integrate what? Okay, what do we think? How do you do? Okay, so then you're going to compare that to the one you're going to do for homework, which would give the exact same value. So the one for homework is the what? dy dx dz. So you compare what you come up with to answer that question for order dy dx dz, and just know that that expression will find the exact same final value as this expression. And I think you'll have a preference. Yeah. No, just set it up. Well, you can't solve because I just said g. You can't solve because I just told you. I'm just saying function g that you don't know. You can't solve anything without knowing that function. But you wouldn't want to, even if I told you the function g. Yeah, but the idea is that when we're changing the order of integration and we're doing it in all the different ways, that the resulting value of all those will be the same. It's just a different approach. Each time it's a different approach in terms of the order of integration. Okay, now let's try something a little harder here. So I want set up a triple integral cylindrical coordinates to integrate this. So hopefully we can get this drawn in 5 or less minutes. We need time to work on it. So outside this, again, got to know your surfaces. If you're stuck, just ask, right? We just got to move, and this isn't the time to learn the surfaces. So if you don't know one, just have the person next to you tell you. But outside x squared plus y squared equals plus c squared equals 1. Inside x squared plus y squared equals 9. Below z equals x squared plus y squared plus 3. And above z equals 0, confined to negative x less than or equal to y less than or equal to x. Go. So it's going to go inside that cylinder, outside the sphere, and beneath that. But then it's confined to this y is less than or equal to, or negative x is less than or equal to. So what is this? What is that? So just in the xy plane, what is that? Y equals negative x, and y equals x. And where is y less than or equal to positive x and greater than or equal to negative x? Where's that? Here. Right? That's what we're talking about in the xy plane. Because y below x and above negative x has to be over here. So there's that thing, and so then do you see it? So what it's below the paraboloid, above the xy plane, outside of the sphere, within the cylinder, and between negative x and x. So it's that thing I've outlined in solid black. What it is. Did anyone have that before I showed it? Something like that? There's another edge here that I missed. Okay, so here we go. We're going to do, did I give you a function? So it's going to be dz, dr, d theta. So the first dz. Arrow is shot from where? Bottom. And comes out? Where's the bottom? For which? The bottom or the top? The bottom is split up. Do you see that? The bottom, the arrow could come in here through this gray portion of the bottom, or it could come in from the bottom through the sphere. So in polar coordinates, what do we have? So in the horizontal plane, we really have it split up like that. Do you see that? So when the bottom z coordinate is the sphere, then our outside double will be projected to here. And when our bottom z limit of integration is coming through the z equals 0, that'll correspond to our outer double being this here. Does that make sense? So we're going to have two triple integrals. Can we do it fast? Sometimes the bottom is 0. What about the top? Does that change, or is it always the same? Always what? R squared plus 3? So when the bottom is 0, what is our outer double integral? It's this part, right? When we come in the bottom through this part here, that's corresponding to this. So that's what you said 1 to 3? R goes from 1 to 3. Theta goes from negative pi over 4 is y equals negative x to pi over 4 is y equals x. And that's dz, so times r. I'll just put the r over here because I don't have room now. All right. And then when the bottom is the sphere, and what is that then? Square root of 1 minus x squared minus y squared. So that's 1 minus r squared, right? Because this is our x squared plus y squared. Right? We've got to change x and y's into r. And it comes out, same place, right? It still comes out r squared plus 3. Then we're talking about this. That's where this happens. 0 to 1. Okay, so a complicated solid, but because we chose cylindrical coordinates, the limits aren't really that bad, right? They're not too bad. Ask me about it on the way out if you need to. Okay, so you got written homework coming Wednesday. You've got a web work due at 5 today, and you'll have a web work due before class Wednesday.